So good afternoon, gang. How you holding up? So today's video is one of a kind, if you will, because it brings me back to my Boston days. I used to live in Boston. I lived there for 7 years almost before moving back to the UK. Actually, moving back to Europe and to the UK, and moving from Cambridge, Massachusetts, to Cambridge, England. Throughout my life, there are three things that I really enjoy doing. One is data, dealing with data and machine learning and analytics in general. Another one, as you can tell from there, is cycling. And the third one is rock and roll. So on my Boston days, I eventually met this one guy, Brian. Brian and I, right, we enjoyed countless discussions about data, countless discussions and miles on our bikes. We also spoke about rock and roll as far as I can remember. However, Onboard data is growing, and a few days ago, Brian and his partner in crime, Ryan, reached out to just showcase to our audience how it could be easy to, create and operationalize a machine learning model starting from, the data with, zero need to create any code, to create a working prototype, and to do it as easy as it would take you to drink an espresso. So yeah, that would be the ultimate goal that I had in mind. So before we move into the actual action with the demo, more a walkthrough, to be honest with you, than a demo, I want to just give you an idea of what is onboard data, right? And what do they do? And, why this could be a very interesting match if you happen to work in building efficiency, energy, sustainability more in general. Wearing the shoes of a data scientist, right? I'm wearing my data scientist hat. I am the end user. The data is far away. And they really bridge the gap for me between, the building and the actual sensor by providing me a unified platform where I can access this data, and this is the first thing. But also, more importantly, they make a pretty remarkable and very significant work of cleansing and normalizing the data, meaning that they will look over the data for me as it comes from the sensor. They will allow me to export and query the data at a fixed time interval, meaning that if the sensor is providing me data at a non-fixed time interval, let's say that it skips a couple of beats and measurements, assuming it measures every 15 seconds, of course, in my time series data set, I will have and I will need to normalize this data at the hourly level, and with onboard data, that is all taken care from them. So it's really remarkable. So without any further ado, let's get going. Onboard data provided me an access to a sandbox. So this is their platform. Quite intuitive, if I have to say. I just explored the data, and I see, and under the office building, I have this air handling unit 1 and 2, where we are capturing quite an amount of data. You see here all the KPIs, and these KPIs are essentially running in real time, right? It's coming up as we speak, boom. So the first challenge would be, can we export this data, or how can we export this data in the easiest way possible? So BigQuery can ingest natively an amount of formats, CSV, Avro, Parquet, and so on and so forth. So something that is really interesting is this data export functionality that I already tried for the most beautiful demo, where essentially I could specify time range and a sampling rate. And this is great. Why is that? Because essentially, onboard data is taking care of the last mile. They are taking care of course, extracting, transforming, and the data from the edge into their data warehouse. And at the same time, they also provided me with a data set that is already cleaned and, more importantly, normalized, because that 60 minutes essentially tells me that I'm going to have all the samples equally spaced, which is incredibly important for ARIMA. On top of that, I'm using the 60 minutes because I feel like it's a good trade-off to start to filter out some of the outliers, right? And of course, this is an example. So the process, I guess, is going to be more important than the actual results. So I'm going to preview the query. And the good thing is that I can export the data as a CSV. So boom, the data has been downloaded. Once it's done, let me see if I can open that up for you. There you go. So this is the shape of the data. So we have one row per each hour. And we're gathering data from two units, AHU2 and AHU1. The temperature looks like to be expressed in Fahrenheit. Otherwise, it's really, really hot. All right, so we got everything we need. Let's move on to BigQuery. So here we are, BigQuery, on the Google Cloud Platform. I already created a project called Onboard Data Demo. So we could land this CSV file into cloud storage and then move it over to BigQuery, but I want to take a shortcut. I can create and load directly, create a table directly as an upload of CSV, Avro, or Parquet, or other formats. So what I have to do is, within the project, I need to create a data set. A data set is essentially a collection of tables, views, models, things like that. And onboard data, that's fine. And the data location, I'll just use the US because our friends are in Boston, and yeah, let's maintain data where the data belongs. I'm gonna create a data set. The data set is ready, and now we can create the table with the data that we just exported. So I'm gonna go here, and I'm gonna do create table. Now, as the source, I can select many things. Cloud storage, Google Drive, Bigtable, Amazon S3. I can have an empty table. I can also upload. I want to upload the file. And I want to upload the file that I just downloaded, time series. Oh, I double downloaded it. Now, the file format is CSV. Yes, it's right. The table, let's call it raw data. It's native table, meaning that it's fully hosted into BigQuery. BigQuery can also federate to external sources. Not going to touch upon that much more. And I'm happy with BigQuery to auto-detect the schema. I'm going to skip the partitioning and clustering. Usually I would have to. This is an example, so I'm going to stick to a non-partitioned, a non-clustered table, even though it's not exactly a good practice. So create a table. The table is going to be created. There is a loading job. Boom, and the table is available. Let me close this. We can already take a look at the data, right? So we had the three fields that we already seen. Take a look some of the technical metadata information. I can also preview the files. This preview file is completely for free. Now, let's run some queries over this data. And the cool thing is that ingesting data into BigQuery is for free. Cool. The second thing is that BigQuery comes with a free tier of querying. So as far as our queries will not be super intensive from the number of bytes processed, we should get away with creating a model for free, right? And I invite you to look over our website to see, Google website to see all the free tiers definitions. All right, so the first thing I want to do, I want to create a time series forecast. So let's start with some queries. So compose a new query. I'm going to create this. So I'm going to create a time forecasting model for the air temperature sensor of just one of the two devices. I took AHU1. It's obviously, I could take either way. So what is interesting is now I can create an ARIMA model through SQL. Let me show you how. So I pre-created the SQL, that's fine. But on our website, the documentation is pretty comprehensive. But the idea is that I'm going to create and replace an entity called a model. Boom. It has a certain name that is completely compliant with objects within BigQuery. So project, dataset, name of the entity. Boom, right? Separated by the dot. Cool. Then some options. We're going to tell BigQuery ML what kind of model we're interested in. And I'm saying I want an ARIMA plus. The timestamp column is called timestamp. The column that I want to forecast is called that thing. And then other configuration parameters, things like if I want to have an auto-tuning of the ARIMA model, if I want to decompose the time series to find seasonality and things like that. So I mean, you can play with them. This set worked fine for me, right, to start with. And then I essentially specify, create this model starting from this data set. Boom, timestamp, and create this model from timestamp and of course that metric that we want to forecast from that table. So let's run it. And this model should take roughly 20 seconds to create, right? So it's pretty fast. We can create this model in an amount of 20 seconds, and we can also see some of the information around, you know, the performance of the model. So the model is created. I can go to the model. This is some metadata. I can look at the evaluation, which is pretty cool. And it's telling me, right, by the variation of P, D, and Q, for those of you familiar with ARIMA, right, what are the resulting performances in terms of AAC, or the lock likelihood, and the variance, and so on and so forth. And of course, the seasonal period that was detected. Now, what can we do with this model? Well, let me not here. Let me just do like this so it's less confusing probably. All right. I can do something like select everything from ml.explain the forecast over a model, our model, right? So onboard data demo, onboard data time series. This 1000 as a horizon is the, the frame over which we want to create the prediction. So 1000 data points in our case essentially means 1000 hours with a specific confidence level of 80%. This explain forecast, there is the explain forecast function and just the forecast function. The explain forecast function is handy because in this case showcases at the same time the actual values and the forecasted values. So this is why I use that. So I can run this forecast. And now we have the complete result sets, right? So we have the timestamp, series type, and if we go all the way to the end of the result set, oops, you can see that the time series type, it's now become forecast. So it's no longer history, it's an actual number. So let me just clean up a bit the columns that I want, right? So I want to have the timestamp. I want to have the data, of course. Let's say I want to have the trend. I want to have the prediction. Oh, let's do like this. It's going to be probably easier. Oops, all right. So I want to have the lower bound and I want to have the upper bound. All right. Just SQL. Boom. I'm running this query. Let me show that it works okay. Yes, it does. It's null for all those samples that are actual. And you know, the prediction interval lower and upper bound have value for all those samples that are predicted. Let's take a look at the data to have a visual about how well it's performing. So I can explore the data using the Visual Studio, Data Studio. It's opening up a new dashboard for me. And now I can literally play around with the samples that we just brought in. All right, so what I can do is I can switch it to a time series. Yeah, these things sometimes happen, but no, don't worry at all. What we're going to do, we're going to say, hey, I just want to have at the first place a date, and that should be fine. All right, now, I'm going to see more in a second. So at the moment, we have the date and the record count, which is not really useful. So let's start with the time series data. I'm going to drag time series data into the metric. So let me remove the time series count and let me move from the sum to the average. Boom. Let me also move this dimension from a date to date and hour. There you go, date hour. Boom. The cool thing is we are also using the BigQuery BI engine, so it's super fast because everything is in memory. This is the actual data that we have. Here there is something very interesting for which we're going to have, you know, just a Scooby snack at the end. Now, let's see the results of the prediction. So first, let's start with the trend. So I'll put in the trend. Average again. The trend looks pretty cool. And then the main event, the lower and upper bound, right? So I'm going to put up this. Lower bound. Again. Let's go with the average. Boom. And the upper bound. Yeah. Oh, I don't have to do the average because now, of course, we're looking at the ultimate resolution. So, as you can see, the prediction is pretty cool, right? So the ARIMA model actually worked, and it works pretty well, even though we moved to things like the date. So if this is a daily prediction, yeah, I need to move the daily prediction, the sum, to an average, of course, right? But the result is consistent. So we have now an operational machine learning model that can be used, right? If you want to create a forecast over the time series. And we created that. How about we want to create an anomaly detection model, right? And because, I mean, when I look and I see this, let me go back to the date and hour. Oops, sorry. Come on, date hour, right? So when I look at this spike right here, yeah, I'm just wondering, can I use machine learning to just identify, maybe receive an alert every time this stuff happens, right? And this could be a reactive alert, or I can count programmatically the number of alerts or of outliers, anomalies that we had over time to predict maybe what kind of sensors can maybe failing, things like that. That's pretty cool. So what I'm going to use is yet another model. So let me just walk you through the thought process. So I'm going to create a new query. Now, I do this, and you see here, I'm also told, I forgot to say, this query will process this amount of kilobytes when run. So you can have an idea of how much money you're burning, and how close you're getting to the limit of the free tier. However, this being said, I'm creating a new model. Now is a k-means model, and I mean, I came up with the easiest model that I could do. For the moment, just a couple of clusters, right? Left or right over the average, above or beyond, right? That was the reasoning, if you will. Yeah, I'm going to use k-means plus as an initialization method, and I'm actually creating this clustering just considering the one dimension that we have. So the AHU1. The AHU2 and the timestamp are not part of the clustering mechanism, of course. So I'm looking at that stream of sample and say, you belong to this cluster, you belong to that cluster. So I'm going to run this. This clustering model, it takes slightly more. So it's going to be ready in roughly 40 seconds. All right, so what can you do in 40 seconds? Call your mom. Call your dad. Call somebody that you love. Make good use. Send them a text, all right? Send them a text. Tell them you love them and you miss them. Alrighty. So 26, 28 seconds, 29 seconds, and so on and so forth. It's moving on. 31, 32, 33, 34. It's moving up. It's moving up. All right, so yeah, 35 seconds. I can go to the model now, which is great. Now, into the model, I can see things like the evaluation, so how the samples were divided, right, within these two clusters. I can take a look at some training information, but more importantly, I can create a new query over this model that I pre-populated. I can use yet another function, ml.detectAnomalies. Bang on. Detect anomalies when applied to a k-means model. Essentially, I have to specify what model I want to detect the anomalies on, then a parameter which is the contamination, and then the table upon which I want to detect the anomalies. Then the result set comes with many samples. Let's start with complete vanilla result sets. All right. So this query is going to take a couple of seconds, even less. So per each and every sample, I know if it's an anomaly or not, right here, true. What I can do now, I can also say, hey, tell me, just give to me those samples for which the contamination parameter make that sample an anomaly, and just order them by timestamp. Because I mean, that's going to be easier for me to see if by running the result set in this way, I can probably look to this error time, which is, between the 16th and the 19th of January. And yeah, you see here, we have many samples, 15th and so on and so forth. So again, this model is far from being super optimal, but with just a couple of SQL statements, we create 2 machine learning models, which is impressive. We could, of course, better tune the hyperparameters. We can do much more. We could deploy these models to an endpoint and just monitor for skew and data drift. We could do a number of things, but the challenge was to create and operationalize a machine learning model in the easiest way possible without writing a line of Python. And actually we did it, because we ingested the data without creating any ETL, just exporting a CSV file and importing it into BigQuery. We created the model by using SQL. And yeah, we took advantage, hopefully, of the free tier of BigQuery. So, to create a prototype, that's a pretty convenient way. Of course, as you scale, there are other considerations to take into account. All right, well, with this being said, I guess the challenge is won. All right. 1, 2, 3, 4. That was it. So many thanks to Ryan and Brian at Onboard Data for giving me the opportunity to talk about this. It was really good. Thank you for sticking around with me. I hope my reasoning made any sense, and maybe you're now willing to just spend some time playing around with data. Thank you very much, and may the force be with you. Bye.